Hello, students. So, we've developed some of the techniques for inverse trigonometry in the past couple lectures, and there was a reason that we developed the techniques of inverse trigonometry is because we wanted to solve trigonometric equations. Now that we have inverse trigonometry, let's solve those trigonometric equations. So, let's do it. Let's try to solve cosine of theta is equal to 1 over 3. And here's going to be the plan. We will find the solutions that actually lie in the unit circle, the ones that we see in the unit circle. Then we'll say, well, those aren't all of them, because if I find one solution to this equation, then I can add 2 pi to that number and get another solution. And if I find the solutions that lie in the unit circle and then add 2 pi's to everything, that will give me all of the solutions. So let's actually do that. So let's try to solve the equation cosine of theta is equal to 1 over 3. Just a good demo. Let's think about inverse trigonometry, and let's think about it pictorially first. So I want, that is a perfect unit circle. If I want cosine of theta equal to 1 over 3, that means in the unit circle, cosine is the x value. I want to know, are there any points on the unit circle which achieve an x value of 1 over 3? Well, let's see. So if there's the line x equals 1 over 3, do you see any places where that line touches the unit circle? Of course you do. You see that one and that one. Now you have a name for one of these. So let's remember inverse trigonometry. Cosine inverse of a number is an angle in quadrant 1 or quadrant 2, or maybe I should say in 0, pi, quadrant 1 or quadrant 2, with cosine of theta equal to star. So, well, let's see. This angle appears to be an angle in quadrant 1 for which cosine is equal to 1/3. So maybe said explicitly, sorry, that took longer than it should have. The inverse cosine of 1 over 3 is an angle in between 0 and pi, with cosine of theta is equal to 1 over 3. So, one solution is given by inverse cosine of 1 over 3. Nice. Well, it looks like there's another solution that I see even in this picture. I see this solution. So, this one is cosine inverse of 1 over 3. How do you find this second angle? Well, how does that second angle differ from the first angle? Well, it looks like it's the exact same, just reflected over the x-axis. So the second one, this angle, this angle will be exactly the negative of that green angle. So the second solution to this equation is given by theta equal to negative cosine inverse of 1 over 3. So there's the second solution. So let's just highlight those two on this graph. So here's one of them. This one is cosine inverse of 1 over 3. This one is negative cosine inverse of 1 over 3. So let's now go back to this unit circle. So those two angles give me all of the solutions that I see in between a single interval of length 2 pi. So those two dots represent the two solutions I see in the unit circle. But there's more than one way I could get to this point on the unit circle. One way is by rotating by inverse cosine of 1/3. Another way is by rotating by 2 pi and then inverse cosine of 1/3. Or rotating backwards by 2 pi and then forward by inverse cosine of 2/3. In general, all of the ways that you can get to this line are given by this angle plus any multiple of 2 pi. So you get an infinite family of solutions by thinking about inverse cosine of 1 over 3 plus any multiple of 2 pi. The other one is given by negative inverse cosine of 1/3, again, plus any multiple of 2 pi. Wonderful. So let's do the same thing. Let's try to solve an equation involving sine. Let's try to solve sine of theta. Let's go with not 1 over 3, let's do 1 over 2. I apologize if you fill in your notes in advance. Actually, you know what? I'm going to fix that in the version that goes online. Alright, so let's try to solve the equation sine of theta is equal to 1 over 2, and we'll start by looking at a unit circle to do it. So there's a unit circle. I want sine of theta equal to 1/2. So that means I want y values of 1/2. So I guess there's the line y equals 1/2. And I want to know what are those two angles. Well, so there are two things that you could notice. You could notice, aha, I keep a copy of the unit circle with me, the unit circle that we filled in class, with me at all times, and I know what angle that is. That angle is an angle of pi over 6. So one solution is given by pi over 6. Those of you who don't keep a unit circle with you at all times would instead have said that this looks like an angle of sine inverse of 1 over 2, which, if you'll remember from the class when we built a lookup table for certain values of inverse sine, you'll recognize that inverse sine of 1/2 is pi over 6. Let's now find this other angle. So this other angle, those of you who looked at the unit circle will say, well, I know what that angle is. This is an angle of 5 pi over 6. So a second solution to this equation is given by 5 pi over 6. Or, if you want the version in full generality, how does this angle differ from that angle? Well, this angle is the same as that angle, but reflected over the y-axis. What corresponds to reflection over the y-axis? Well, doing the operation pi minus that angle theta. So I guess more analytically, the other solution is going to use the fact that the sine of pi minus theta is the same as the sine of theta to see that pi minus pi over 6 is another solution. That's the same thing as 5 pi over 6. Now that we found the two solutions we see in the unit circle, we can get all of the solutions by adding 2 pi k's. The set of all of the solutions to the equation sine of theta is equal to 1 over 2 is given by theta equal to pi over 6 plus 2 pi k and 5 pi over 6. Over 6, excuse me, had to sneeze. Plus 2 pi k. Nice, so let's just put this into the form of a flowchart. If someone asks you to solve an equation of the form cosine of x is equal to c, where c is any constant, well, there are three trivial cases first. If c happens to be bigger than 1 in absolute value, then there are no solutions. Let's see why using a unit circle. So this will be in yellow out here. So if you draw a unit circle, and someone asks you to solve cosine of theta is equal to 2, well, if there's the line at x equals 2, how many times does that line cross the unit circle? It doesn't. There are no points of intersection, so that means there are no solutions. Whenever you take an x value that's bigger than 1 in absolute value, there will be no solutions. If you want to solve c is equal to 1, so next let's try to solve cosine theta equals 1 on the same picture. Well, there's an x value of 1. So in the unit circle I see a single solution. I see an angle of 0, or maybe pi, depending on how you prefer to draw it, 2 pi, how you draw your unit circle. So I see a single solution in the actual picture. This point is the only solution I see. That point now corresponds to infinitely many angles. It corresponds to the angles that look like multiple of 2 pi. So the general solution to the equation cosine of theta equal to 1 is 2 pi k. If you want to solve the equation cosine of theta is equal to negative 1, well, let's do that too. If you want to solve cosine of theta equals negative 1, you'll draw a line at y equals negative 1. You'll see, yeah, that's an angle of pi is the only angle in the unit circle in between 0 and 2 pi, which produces that x value. Well, that's fine. There's the one that lies in the unit circle. You can find all of them by adding 2 pi k's. So the general solution will be x plus 2 pi k. The general case, if someone asks you to solve cosine of x is equal to c and they haven't just given you a silly problem, they'll be asking you to solve cosine of x is equal to c for a number. So otherwise, i.e. c is in negative 1 to 1. That is, absolute value of c is less than 1. So you'll find, so let's, that picture is getting crowded. Let's draw a new one. If you want to solve, so let's take, I don't know, that one. So if I want to solve cosine of theta equal to c, well, there's the line at x equals c. How many points are there where this line crosses the unit circle? There are 2. So find angles which correspond to those 2 points. Those angles are inverse cosine of c and negative inverse cosine of c. This angle is inverse cosine of c. This angle is negative inverse cosine of c. Once you find those 2 starting solutions, and simplifying if possible, right? Did I say cosine? Okay, good. Find those 2 starting solutions and simplify if possible. If you happen to, that happens to be a number whose inverse cosine you know, then use that fact. So what do I mean by simplify? For instance, if you have the inverse cosine of the square root of 2 over 2, you know that the inverse cosine of the square root of 2 over 2 is pi over 4. So simplify if possible. Then the general solution, just take those solutions, add 2 pi k's to them. Very good. Same thing for sine. If you want to solve the equation sine of x is equal to c, so that's c for constant, not c for cosine. C for constant. That's not necessarily important to your understanding, but that's why I chose the letter c. Similarly to before, if c is bigger than 1, well, you draw a unit circle. There's the unit circle. If I want to solve sine of theta equal to 2, 1.5, something bigger than 1. Well, remember, sine is the y value, so I'll draw a line at y equals 1.5. That line never crosses the unit circle, so there are no solutions. If c is equal to 1, there's the line at c is equal to 1, and if this unit circle had been drawn correctly, you would be able to see that, oh, the only solution I see in between 0 and 2 pi is pi over 2. So your starting solution is pi over 2. To get all the solutions, add 2 pi k's. If you want to solve sine of theta is equal to negative 1, well, there's the line y equals negative 1. This angle seems to correspond to 3 pi over 2, or negative pi over 2, depending on your preference. So your starting solution will then be negative pi over 2 plus 2 pi k, or negative pi over 2 plus 2 pi k. That will be fixed in the online version. Or, of course, if you prefer, 3 pi over 2 plus 2 pi k. You'll get the same family of solutions out of that. So let's just check that really quickly, because those are both reasonable solutions to write down. Let's write down what some of them would be. So this one will give negative pi over 2. It'll give negative pi over 2 plus 2 pi, which simplifies to, let's see, that's 2 pi's minus half a pi. That's 3 pi over 2. It will give negative pi over 2 plus 4 pi. And let's see, that's 8 pi over 2 minus pi over 2. That's 7 pi over 2. And so on. The second family of solutions will give 3 pi over 2, or 3 pi over 2 plus 2 pi. So let's see, 2 pi is 4 pi over 2, so that'll total 7 pi over 2. The next one will give 3 pi over 2 plus 4 pi. That will be 11 pi over 2. And so a thing to notice is these family of solutions are the same. Those two are the same. These two are the same. The next one in the list would be the same as that one. The previous one in this list would be the same as that one. So these two families of solutions may look different, but they are the same. And then the general case, if someone asks you to solve sine of theta is equal to c, where c is a number between -1 and 1, I'll draw that line. There will be one of the solutions. That'll be the inverse sine of c. Then there will be the one that you get by reflecting over the x-axis, but how do you reflect over the x-axis? You do so by doing pi minus inverse sine of c. Very good. By comparison, and then add 2 pi k's, right? So your general solution will be x equal to the inverse sine of c plus 2 pi k, and pi minus the inverse sine of c plus 2 pi k. If you want to solve an equation that involves the tangent, well, that is, by comparison, fairly simple. So let's remember what the graph of y equals tangent looks like. It goes and so on. The sound effects were very important. So if you want to solve tangent equal to any constant, well, let's draw that line at y equals c. It looks like no matter what c is, I will see infinitely many solutions. And these solutions will be very nice in that, what's the period of tangent? It's pi. So these solutions will all be separated by exactly pi. So if I can write down one of the solutions, then I can get all of them by adding pi k's. Well, I know one of them, right? This bit is the bit that I invert to get inverse tangent. So this solution will be tangent inverse of c. And then to get all the solutions, just add pi k's. To solve tangent of x is equal to c, your starting solution will be the inverse tangent of c. Simplify if possible. For example, the inverse tangent of 1 is equal to pi over 4. So if you happen to want to solve tangent of x is equal to 1, your starting solution will be pi over 4, because that's the inverse tangent of 1. So let's use this algorithm to solve one more simple trig equation, and then we'll move on to complicated trig equations. All right, well, let's start with this. Tangent of x is equal to -8. So let's follow this algorithm. Starting solution is the inverse tangent of -8. Then I add pi k's. So the solution to tangent of x is equal to -8 is given by x is equal to inverse tangent of -8 plus pi k. Let's solve. Sine of x is equal to -1/2. So, following this, the two starting solutions will be inverse sine of -1/2 and pi minus the inverse sine of -1/2. Then we'll add 2 pi k's. So to solve the sine of x is equal to -1/2, we'll get inverse sine of -1/2 plus 2 pi k. And we'll also have pi minus inverse sine of -1/2 plus 2 pi k. However, think for a second, is -1/2 a y value that you see in the unit circle? Take a look at the unit circle you keep with you. It is, isn't it? What angle produces that result, that value for sine? Well, -pi/6 does. So this is really -pi/6 plus 2 pi k. And this is pi minus -pi/6 plus 2 pi k. So really, the solutions are x is equal to pi/6, -pi/6 plus 2 pi k, or 5 pi/6 plus 2 pi k. Now, those of you who went and did this one on your own may have found a different looking family of solutions. Instead of this family of solutions, I'll do this off to the side, you may have gotten y equal to 11 pi over 6 plus 2 pi k. But let's compare these. Sorry, x. Compare. So let's see. In the first family of solutions, I see negative pi over 6. I see negative pi over 6 plus 2 pi. Now let's actually go the other way. I see negative pi over 6 minus 2 pi. Let's do the same. So let's simplify these two things on either extreme. So let's see, 2 pi is 12 pi over 6. So this will give me 11 pi over 6. This one will give me, I guess, negative 13 pi over 6. Now, let's check out the other solution that you may have gotten. It contains 11 pi over 6. It contains 11 pi over 6 plus 2 pi. Well, again, 2 pi is 12 pi over 6, so that's 23 pi over 6. Over here we see 11 pi over 6 minus 2 pi. Let's see, again, 2 pi is 12 pi over 6, so I guess that leaves me with negative pi over 6. And notice there's some overlap. This 11 pi over 6 appears as the starting solution in this family of solutions. This starting solution appears as that element of the second family of solutions. If I went one more to the right, I would see this 23 pi over 6 appearing as that solution in the green. This negative 13 pi over 6 would appear as the previous solution in the blue. So these two give the same family as the solutions, they're just shifted by one. So they're both correct. Finally, let's solve tangent of x is equal to the square root of 3. So let's do it. So following this algorithm, this tells me exactly what the answer should be. The answer should be x equal to tangent inverse of the square root of 3, square root of 3 plus pi k. But now, look at the unit circle. Do you see a point on the unit circle where the slope of the line from the origin to that point is the square root of 3? You do, right? So you have this point up here, which is at 1/2 comma root 3 over 2. The slope of that line, which remember is tangent, is the square root of 3. So that means the inverse tangent of the square root of 3 is pi over 3. Nice. So that completes the first part of the lecture in which I talk about how to solve simple trig equations. We will go on in the second part of this lecture to figure out how to solve complicated trig equations. So I'll put this up and I'll come right back to you. See you in the next one.